Welcome to NASA Edge.
An inside and outside look at all things NASA.
You know, Chris, I'm super excited about the test coverage today because, as you know, I'm a big fan of transits. But the thought of being able to witness or capture these transits all across the galaxy, pretty impressive.
Yeah, it's pretty cool. You know, over the course of the next 30 minutes, we're going to be looking at all aspects of the test mission, from the science, engineering, spacecraft, and the launch vehicle.
That's right, Chris. And to get things started, we want to take a broad introductory look at the mission. We're here at NASA Goddard Space Flight Center with Jeff Volosin, the project manager for TESS, the Transiting Exoplanet Survey Satellite. Jeff, this is a very exciting mission looking at exoplanets. Tell us, what is the TESS mission?
So it's another mission in NASA's effort to learn more about planets outside our solar system. So it's kind of an evolution, right? When I went to college, there was no such thing as an exoplanet. One had never been found. Nobody thought there'd ever be one found because they're so small compared to the stars that they go around. So when the Kepler mission flew, maybe 10 or 15 years ago, all of a sudden, thousands of exoplanets were discovered, that there were these orbiting planets around stars outside the solar system, that some of them were as small as the Earth even. So Kepler was able to find planets, mostly larger ones, and they focused on one area of the sky. So for years, they just looked at one area. So we knew that there's now lots of planets, and probably everywhere you look, there are lots of planets. So our mission is a survey mission. So the TESS has a survey word in it. And survey is all about, we want to look through the whole sky. So we're not going to just look in one spot. We're going to look all around the sky over a 2-year period and look for planets. We have very sensitive cameras. We're going to look for Earth-like planets that are closer to Earth. Now, by being closer to Earth, it allows further follow-up study. Because if you could find planets orbiting stars that aren't that far away, now the James Webb Telescope, with its big, powerful mirror, can say, okay, I know TESS has told me there's a small Earth-like planet around that nearby star. I'm going to go ahead and focus my powerful telescope. And what happens now is when the planet goes in front of the star, you can actually see the light going through the atmosphere, coming to Earth, and then the spectrum of that atmosphere is available. And the spectrum being what parts of the starlight were absorbed by the planet's atmosphere. And that'll tell you, is there carbon dioxide in the atmosphere? Is there oxygen in the atmosphere? So all of a sudden you can learn about an Earth-like planet and what atmosphere it has.
So is TESS then really sort of putting out this map of potential planets for James Webb?
Yeah, exactly. So that's where we fit in, right? So Kepler proved that you could find stars almost anywhere you look that have planets around them. Kepler showed that there's a variety of different types of solar systems that we never would have imagined, and that there are Earth-like planets out there. Now with a very sensitive set of cameras on TESS, we have 4 cameras on the spacecraft that'll look out at a wider swath of the sky, and then every month or two we'll move and look at a different part of the sky. But one thing we're going to focus on is looking straight up. Think of it as a north ecliptic pole, and that's a place where the James Webb Telescope can stare at that spot with the sunlight not getting in the way of the observation. So that's a place they would like to look for exoplanets, because if you're going to look at the atmosphere of one of these exoplanets, you have to stare for quite a long time every time the planet goes in front of the star. So it's great if they have these objects available straight up in the north ecliptic pole or straight down. So that's a lot of our focus. And so the goal is to find them candidates to look at.
And it seems like this is vastly different from Kepler in that it is doing this complete, 360 full range. I don't know how to describe it.
Right, yeah, a whole sky survey.
Yeah.
And the great thing about that is, imagine what Kepler was able to find just blew everybody's minds. Planets that might be all diamond, planets that might have totally water surfaces. Imagine what we'll find when we now look all over the place. Kepler looked at one little area and found all that. And we can't even, begin to think about what are we going to find in the survey over a couple of years. So yeah, that's the exciting part of that. And the other thing is, what we'll find out is how big these planets are. So when you see the light being blocked, all you can tell is the size of the planet compared to the star. You can't tell how heavy it is. And if you can't tell how heavy it is, you really can't tell what it's made of. So what we're going to do is ground telescopes can actually look at those same targets. They look at the planet's effect on the star. So you think about TESS as looking at light being blocked. Well, what the ground telescopes are doing is the star is wiggling a little bit as it's spinning around because the planets are tugging on it. The heavier the planet, the more it tugs on the star. That wiggle is really small, but those ground telescopes can quantify the wiggle and then tell you how heavy the planet had to be. So now you have the size of the planet and the heaviness of the planet, and you can get the density and figure out, is it water, is it solid, is it gas?
Earth-like would be fantastic, but if we find, say, a desert planet, is there, I mean, what is the likelihood that we can just go ahead, name it Tatooine, and be good to go?
Yeah, there's a lot of people who are looking for, name your favorite sci-fi movie, right? A lot of people are looking for their favorite sci-fi movie planet, but I think we're gonna find that there's probably even more diversity than sci-fi writers have ever thought up. And I think that's already what we've seen from Kepler, is that there's some really weird planets out there. So I think that's what we're looking forward to.
Joining us now is Tom Barclay, who's a TESS scientist. What exactly is a TESS scientist?
So I'm working on this new mission, the Transiting Exoplanet Survey Satellite, and my goal is to try and find the planets in the data. So what have I been doing in the last year? We don't have any data yet.
Yeah, that's a good question.
So I've been trying to simulate what we might find, because we have to plan a lot of follow-up observations. We use a lot of ground-based telescopes. We also use other space-based telescopes. So we have to plan what we think we'll find, so we know what data we want to collect. So I've been simulating, but soon I get to stop simulating and I get to do the real thing.
Well, I want to talk about that too, but I'm wondering, how do you simulate something like this? Do you look at planets you already know data for?
Pretty much, yeah. We already have an idea of the stars TESS will look like. We have an idea of how common planets are, so we guess how many we might find and pass it through our system of how we understand the telescope will work.
Well, now, it's interesting. You said you were very excited. Obviously, I could totally understand why, because I share that enthusiasm. But getting that data back, what kind of things do you expect to see from the TESS satellite initially in terms of data?
Yeah, our most exciting thing is when the first planets start to come in. These are going to be relatively small planets we think we'll find around bright stars. Our goal here is to find our nearest neighbors, find planets orbiting the brightest and nearest stars to us, ones that we can really study in great detail using other telescopes.
So, after TESS is done and they've identified these planets, we could have maybe on the order of, say, hundreds of candidate planets, if you will?
Actually, we expect to find thousands of planets, of which several hundred will be smaller than about twice the size of Earth. And twice the size of Earth is interesting, is because that's when you start to become rocky. Things somewhere between what the size of Earth and about twice the size of Earth is this break between a rocky planet and somewhere that's got a significant amount of gas in its atmosphere, much, much thicker than our own.
Thank you so much, Tom, for being on the show. Great information. Looking forward for a great launch today.
Yeah, I couldn't be more excited.
Yes, and about a month ago, Chris had an opportunity to learn even more about the science behind TESS.
We're here with Stephen Rinehart, the project scientist for TESS. How you doing, Stephen?
Not too bad.
How are you able to detect that transit from millions and millions of miles away? Because when we've seen the Venus transit, when you see that pretty up close with binoculars, you can see it even live, but how can you see something millions of miles away?
Right, well, the Venus transit is a perfect example. Okay. When you watch that, if you watch a video from some of the other NASA missions, you can see this black spot passing across the face of the sun. Well, now imagine that the sun were just farther away. You don't see the spot anymore. You can't resolve it with binoculars or a telescope or anything else we've got right now. But what you can do is you can see that the star gets so very little fainter. For instance, if you have Jupiter passing in front of our sun, you see about 1% of the light from the star gets blocked by Jupiter. So if you were watching that star very carefully and were very, very far away, you would see that the light just suddenly drops and then comes back again. And so that's the signal we're looking for. We're looking for that little drop in brightness, and we're looking for it to happen regularly, right? If you, for instance, have Earth around the sun, once every year, it would pass in front of the star and block that light. So you're looking for this repeated small dip in the brightness of the star.
So given that, looking at the brightness, I mean, you have to have pretty sensitive cameras to be able to detect that dip.
That's right. So, I said Jupiter's 1%. Earth around the sun is 1/100th of 1%, or 100 parts per million.
Wow.
So what TESS is designed to do, those cameras are designed to be exquisitely sensitive so that we can detect things that are small changes less than 100 parts per million. And really the thing that dominates a lot of the uncertainty are the stars themselves. Stars are not quiet at the tens parts per million level. So you've got this stellar noise, and then you've got the sensitivity of the cameras, but together we should be able to detect small Earth-sized planets around stars like the sun and even smaller than the sun.
Now I understand you're going to be looking at something like 200,000 stars in that 2-year mission. Are you picking out those stars, or are you just kind of going to a region and say, look, we're just going to look for opportunities in a certain region?
So it's a predetermined list except where it's not. Most of this list is, there's a group of the science team that have worked on a thing called the TIC, the Test Input Catalog. And the TIC has about 3 billion stars, if I remember my numbers correctly, in it. Obviously, we're not going to be looking at all those. Right. It's every bright object in the sky down to a certain brightness level. It's huge. But then there's the actual target list. And that's between 100 and 200,000 stars. And these are stars that are specially selected for specific observations with TESS using a 2-minute cadence. So every 2 minutes, they measure the brightness of that star. And those are the stars that have the highest likelihood that we'll actually be able to find an Earth-sized planet around them. So stars that are smaller, it's easier to find smaller planets around smaller stars. Stars that are brighter, and so on. In addition to that, there are additional stars that are proposed by members of the general community through the guest investigator program, and that means that we can observe some other stars that were not necessarily viewed as great targets by the science team, but which somebody out in the community says there's a good reason to look at this star, so we will. And in addition to that, we have the full frame images. So every 30 minutes, TESS takes a picture of the entire field of view, which is 24 by 96 degrees.
Wow.
Huge. And with that, we're going to be able to find a lot more planets. Now, most of those planets are going to be the large planets. They're going to be Jupiter-sized planets and so on. But it's going to, about 10 times as many of those in the full-frame images than the number of planets that we'll find in those postage stamp data, which are really focused on trying to find the smaller planets.
Now, look at our solar system. Our sun is an average star. Are you kind of targeting those type of stars for possible Earth-like planets, or could you have stars that are much bigger than our sun that could potentially have an Earth-like planet?
So, first off, let me say that when we say that our sun is average, we are really wrong. Our sun is actually kind of unusual. It is a sort of average in size, but it's not actually very active compared to most stars. Oh, wow. And there's a lot of other stars out there that are very, very different. So a lot of the stars that TESS will observe are what we call the M dwarfs. So these are much smaller than the sun. They're much cooler than the sun. So for instance, the habitable zone, that region around the star where you could have liquid water on the surface of a planet, is much, much smaller than you have around the sun. Those are going to be very good targets for TESS because they're smaller. The larger stars, if you start talking about some of the stars that are a few times bigger than the sun, the problem is that now trying to find a small planet around this big star,
right,
it gets really hard. All right, imagine that you have a star that's 3 times bigger than the sun, but you have that same planet, then suddenly it's 1/10 of the as easy to detect as it was before. So while we will look at some of those, it's going to be really hard to find the smaller planets around those kinds of stars. But those are important observations to make because we haven't done a lot of observations of those larger stars looking for exoplanets yet because they're hard. And so we really don't know what the population of planets looks like around those kinds of stars.
Joining us now is Natalia Guerrero, test scientist at MIT. How you doing, Natalia?
I'm doing great. It's great to be here.
I tell you what, Stephen did a great job talking about the TESS mission. And what I want to focus in on is all the data that you're going to be collecting from the spacecraft. You're going to be collecting a lot of data over the course of the next 2 years. I mean, how are you going to be able to just kind of sift through all that data?
Right. So we get down 2-minute and 30-minute images from the spacecraft, and the 2-minute images are what go to the data processing center at NASA Ames. And this is a pipeline that's actually very similar to the pipeline that was used to search for transits in the Kepler data. So the data will be processed at NASA Ames and comes back to MIT to be processed, and we will then look for TESS objects of interest. And so these are any objects, including exoplanets, which is what we're really interested in, as well as other types of astrophysical phenomena that cause transits, such as eclipsing binaries or other types of stellar variability. And it's going to be a really exciting and busy time for us.
Now, is it a fine line in determining if it is actually an exoplanet or if it's a binary or some other object in space?
Sometimes it can be, so that's why we're relying on the experience of so many of the observers at MIT and at the Harvard Center for Astrophysics, SAO, who are working together at the TESS Science Office to identify these exoplanet transits. It's really, right now, the most efficient way to do it is by eye. So we're going to have people going through kind of by hand and looking through each sector's worth of transits. And then as we get more of an understanding of the test data and the systematics within it, we will be able to start moving towards automation.
I mean, is that a long process? Doing it by essentially by hand or with the human?
You'd be surprised. Yeah. There's some observers who are really quick, who are able to just move through like hundreds of these transits in a couple of hours. It's very impressive.
Well, Natalia, thank you so much for joining today, and I can't wait till you get the first set of data and you start sifting your way through and see if we can find some Earth-like planets.
Yeah, I'm really, really excited. Looking forward to it.
You know, Franklin had a chance to learn more about the test spacecraft and see what it takes to actually make it ready for flight.
Hey, today I'm hanging out with Robert Lockwood, who was the spacecraft program manager from Orbital ATK for tests.
Hey, Franklin.
Hey, man, we are going to go over to this big building. Is this a high bay or a clean room?
Yeah, it is. It's a big high bay clean room. It's the Payload Hazardous Servicing Facility.
Once I get in there, I'm going to do a little bit of a B-roll for our show, but also we'll have an opportunity to do an interview.
Okay.
Do I have to put on a bunny suit?
Yeah, you do. You're going to get all covered up. The main source of contamination for spacecraft is people. So we're going to cover you all up in a bunny suit, going to put a mask over your face, but you'll still look pretty.
Oh, I'm glad I saved lunch for after the interview. So Robert, we're here in this high bay clean room. What types of tests or checkouts are done for tests in this facility?
Well, primarily in this facility is for propellant fueling. We're going to fuel the vehicle with 45 kilograms of hydrazine to perform our on-orbit maneuvers. This facility is certified for propellant fueling, so that's primarily why we're in here. We also have other performance tests that we do. Check it out after it went from Dulles to here, make sure everything worked after shipment, deploy the solar arrays and stow them. We also do a number of checkouts and closeouts. One of the things they're doing today is putting the vehicle on a high stand so that we have easier access under the vehicle to close out some of the parts on the bottom part of the vehicle. When our partners from SpaceX arrive here with the fairing, we will attach the vehicle to the fairing, encapsulate it, and then they will transport it over to Space Launch Complex 40 for launch.
As a program manager for tests, tell me about some of your duties.
Primary among those are moving all the little parts around, the logistics for keeping things on schedule, keeping staff working in the areas they need to, interacting with all of our partners at MIT, at Goddard Space Flight Center, to make sure that things just keep moving smoothly towards launch.
See, when you talk about partners, you receive components for tests from all over the country, but when you talk about MIT, they are responsible for pretty much the major part of the satellite, the cameras, is that right?
That's right. So we have one instrument. It's comprised of 4 wide field of view CCD cameras. Those are manufactured at MIT Lincoln Laboratory and then delivered to us for integration.
And integration was done at Orbital in Dulles, Virginia, right?
That's right. We have a full facility there for integrating all the parts and testing it.
Talk to me a little bit about the testing. I know that there is environmental testing done for all satellites. Can you tell us a little bit about the process that tests went through at Orbital?
Sure. We received the 4 cameras sitting on its camera plate and integrated it to the top of our spacecraft bus to form a full observatory. Then we take it through a set of comprehensive functional tests just to make sure that everything is working correctly. We then put it on a shaker table or vibration facility where we shake it at levels that simulate launch environments. We put it in a chamber to test it for electromagnetic compatibility. Then we put it in a thermal vacuum chamber to expose it to the highs and lows, hots and colds of on-orbit environments.
Robert, did you encounter any obstacles along the way managing this program?
None to really call out. It's the typical thing when you put spacecraft together in a facility like Dulles, Virginia. There are a number of spacecraft processing through there. So it's a continual shell game when your part is ready to go integrate or when your part's ready to go onto the vibe table for test or into the TVAC chamber. But no obstacles that really stopped us from getting here on time. And in fact, we've got about 3 weeks of margin to sit around now. So we're actually even a little early.
I tell you, Franklin looks really good in the bunny suit, but you know what else? Those dance moves going into the clean room, pretty impressive, right?
You know, we've been doing this for about 10 years. I've never seen dance moves from Franklin like that. You know, for the past 20 minutes, we've been looking at all aspects of the test mission, the science, the engineering, the spacecraft. Let's turn our attention now to the launch vehicle and SpaceX's Falcon 9.
And if you want to talk about the launch vehicle, then you have to go to Launch Services Program, LSP. So let's go to Tiffany now, who's out at the Causeway.
That's right, Blair. We are here at the NASA Causeway. We're about 4 miles away from Pad 40. I have Denton Gibson here with me. He's the Vehicle Systems Engineer for the Falcon 9. Denton, welcome to NASA Edge Show.
Thank you. I'm excited to be here. It's launch day.
Yes, it is. Robert had mentioned earlier about the PHSF, and LSP owns that. Can you tell us a little bit about that processing facility and LSP's role?
So LSP is the organization that matches the spacecraft to the launch vehicle, and LSP also oversees the integration of the spacecraft to the launch vehicle. And the PHSF is one of the facilities that LSP oversees, and that is where the test spacecraft has been processed.
Tell us about the Falcon 9 and the stages of it.
So the Falcon 9 is one of the newest rockets in LSP's fleet, and it's a two-stage rocket. The first stage has 9 engines, which is a lot of engines, more engines than most of our other launch vehicles has. And amongst those 9 engines, it produces 1.7 million pounds of thrust, which is about 100 F-16s. The second stage has a single engine, and then it has a payload fairing which protects the spacecraft as it's flying through the atmosphere.
Now, there's a significance about the Falcon 9 rocket. Can you share what the uniqueness is of that rocket?
Yes, we have a lot of unique things about this rocket, but 2 particular things I want to talk about is the payload fairing has an attitude control system that allows the fairing to be recovered for a future use. And then the best thing about this vehicle is the first stage can flip itself over and fly itself back to either a landing pad here at Cape Canaveral or a drone ship that's off the coast in the Atlantic. Unfortunately, the first stage is going to land at a drone ship in the Atlantic Ocean on this one, so we're not going to get to see it back here at Cape Canaveral.
Denton and I are both good for launch, or go for launch, I said.
Absolutely.
And we're going to send it back to you guys at Hangar AE.
5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying Tess, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
What a great launch by the Falcon 9 launch vehicle. And as Tess gets into orbit, the only thing I can say is let the planet hunting begin.
You gotta love the fact that we are now poised to discover new planets, Earth-like planets.
In a couple of years, when James Webb is in space, we'll be able to see the fruits of Tess's labor through Webb's images.
And on that note, you're watching NASA Edge.
An inside and outside look
At all things NASA.